So today we're going to do something a little different and talk about how to think about the correctness of the parallel programs that we're writing, and specifically how to think about the correctness of data structures that are shared by a number of different threads that need to access them without necessarily having any pre-planned synchronization that is making sure that they can asynchronously access those data structures. So the concept we'll talk about near the end is called linearizability. But generally, I'm going to talk here about what it means for these data structures to be correct. So last time, I talked about load balancing, and that one of the techniques for load balancing, essentially the technique of last resort, when you really don't know what the load of each one of the computations associated with a piece of data will be, or you don't have the ability to see what kinds of work is going to unfold in something like a game tree, or there's high variability, so you can't predict the cost of things, is to use work stealing. And in work stealing, we put the tasks to be done. That's usually a data structure that we're working on. It might be just something as simple as an index that says work on this part of a matrix, or it could be something that is much more complicated, like a piece of a data structure that has some state in it. But we'll probably put pointers into this task queue of some kind. And so a task queue is then shared by all of the processors, which are called workers, and they pull things out. So now, and work on them and then put other things back in again. So the question then is, how do you build something like one of these task queues? OpenMP actually does build into the runtime system for OpenMP a task queue, but it's something that you may face in terms of writing other parallel programs, so it's useful to understand how one goes about writing something like this. And then what do we mean for it to be correct? So for serial programs, we know sort of what it means for a queue to be correct. We can write it down formally if we want to, but in the case of a queue, if we know that it's a FIFO queue, we know the first thing we put into it should be the first thing we get out of it, a first in, first out queue. We know that a stack is a first in, last out data structure. We may also know some things by looking at the comments, hopefully, in the methods that say something like, well, you can't pop an element off of an empty stack, it'll throw an exception or whatever. And you can look for something that's in a search tree, but if it's not there, you're not going to find it. So those would all be part of really a specification. It should be in the comments of that data structure, and we could formalize it more if we wanted to. For parallel programming, if we wanted to take these data structures, such as a stack or a queue or a search tree, and put them into a parallel program, we could just decide up front that only one processor is going to access that data structure. And if that's the case, then these data structures you built in, say, 61B will work just fine. But another thing we can do is to try to make it thread safe, which means that we'll put synchronization of some kind inside the data structure so that it will work correctly, even if we have multiple threads that are trying to access it and they're not coordinated at all. That is, they're just asynchronously trying to do NQs and DQs or pushes and pops or whatever. So a lot of what I'm going to talk about, and especially the pictures on today's slides, are coming from a great book by Morris Herlihy, who was a graduate student with me many years ago at MIT, and Nir Shavit, who is now on the faculty at MIT, and Morris is on the faculty at Brown. So they wrote this book on the art of multiprocessor programming, and I recommend it. And by the way, it's available online if you don't want to go and buy it, but you might want to look at a couple of the chapters, because we will be talking about this material at least for a couple of weeks in next lecture or two, and also you may have some homework and quiz questions on it. So it is available online, though. And this is the standard acknowledgement that I'm just including in here that says it's releasable, and the slides are something that I can reuse, which I have, and adapted and hopefully not introduced any bugs. Their code was all written in Java, so I will show you code written in C++. Okay, so we've got a current computation, and what that means is we've got a set of processors here. These little chips are supposed to be processors, and we've got 3 of them, and they're accessing data structures that are in shared memory, and this could be these could be objects that are things like linked lists. It could be a search tree, or whatever these objects are, but all of the processors can access those shared data structures. And that computation is concurrent The overall application in this case that we're looking at in this class is something that's a parallel application. Remember, it's something where we're trying to get more speed. We're trying to make it run faster by using parallelism, but it may come down to something like a task queue where you have a bunch of independent work that you can do to make the code run faster, but somehow you need to share it across the processor, so you need a queue data structure. And so this is a concurrent object that's going to have asynchronous access to calling the methods without necessarily synchronizing before you call each one of the methods. So how do we describe one of these concurrent data structures? How do we implement them? And how do we know if we've got a good implementation? How do we know if it's correct or if it's right? Well, today we're mostly going to talk about the first two, the first and the third. How do we describe it, and how do we tell whether or not we've got a good implementation? So I'm going to use the example of a FIFO queue. So here we've got our one processor that's putting things into a FIFO queue, and we know that when the order it puts them in will be the order that it takes it out. So I'm going to assume that you sort of have an intuitive idea of what the specification of a sequential queue looks like, a serial queue that only one thread is accessing. And we're going to build on that to try to understand what it looks like in parallel. So the dequeue method, for example, is going to, and there's a little notation we'll see later, at least later next week. If we do a dequeue operation, we know that the thing that will come out of it is this blue object, whatever that is, that was at the head of the queue. Now we'll talk about an implementation of it so that I can show you a little bit of code, and it's closely related to the code that you'll be working on in lab this week. And here we have a circular queue, which I'm drawing this way. It'll be an array in memory, and that array in this case has 8 elements in it, so it's a pretty small queue. And it's got a head pointer and a tail pointer, where the head points to the first thing or the oldest thing in the queue, and the tail pointer points to the space just after the newest thing in the queue. And we're going to protect these fields, the head and the tail, and then there's going to have to be a data structure to hold the list itself, the array itself of elements, and they're all going to be protected by some locking. So here's what our queue class looks like in C++. And we're going to really simplify this for lecture. We're not making it a template type, so it's going to just be a queue of integers. And furthermore, I'm going to assume that I'm only going to put positive integers into this queue, or at least non-negative integers into the queue. And you'll see a little bit why I'm assuming that. It's just to simplify the code a bit for the purposes of being able to cram it onto a PowerPoint slide. So here's our little circular queue. What is the state inside of that? Well, it's got an int, which is the capacity of the queue. We've got the head and the tail that we've talked about. And then we've got the items, which are all of these blue items that live around this ring. Here it's just a vector. And then we're going to have a lock, which is an OpenMP lock here. In lab, you may be looking at C++ style locks that are built in to one of the standard libraries, but either one of these will do in this particular case. And these fields are going to be protected by this lock. And I haven't highlighted capacity because capacity is going to be fixed. We're never going to change the size of our queue. If it fills up, we just won't be able to put anything else into it. And so that doesn't need to be protected by a lock, as we'll see. So here's what the constructor looks like. It creates a new queue with some given capacity. As I said, in this particular case, the capacity is 8. And it sets the head and the tail both to the 0th element. It sets the capacity equal to whatever is passed in. And we're not going to modify that again. And so that's why we won't need to worry about locking. We also don't need to worry about locking in this constructor because only one thread is actually executing this code in the constructor, and then is going to, at the very end, return a pointer to the object that was filled in. And so in addition to setting the head and the tail pointers to 0 each of them, it's going to create a vector of size capacity which holds the items. And then it's going to initialize the lock. Remember last time we talked a little bit about synchronization, and you do need to initialize your locks. Okay, so what are the queue operations? Well, if you've got 2 processors, and the way we're going to implement this actually in this lecture, which is not going to be a very sophisticated implementation, it's actually going to lock basically the entire method. And so one processor at a time is going to have a chance to access the queue. And this red processor, for example, is going to acquire the lock, turning it red, and then it can manipulate the elements of the queue, the items, and the head and the tail pointer. Whereas this one, if it tries to acquire the lock, is just going to end up waiting. Okay, so here's the code for the NQ operation. So I'm going to first look at the non-locking part of the code, just look at what it would look like in a serial implementation, just so we're all on the same page. So the first thing we'll do in an NQ operation is make sure there's space. We check to see whether the tail minus the head is equal to the capacity, in which case there's no more space in the queue. And so that means that we'll just return false. If there is space, then what we'll do is to put elem, the thing that's passed into the tail, the position of the tail, modulo the capacity, so this thing will wrap around in a ring, that's why we've drawn it as a ring, and then increment the tail pointer. And now we do need to synchronize this if we want to make sure that it works in a concurrent setting where multiple threads may be accessing it. In this particular implementation, I'll use a very simple strategy, which is to just acquire the lock as the first thing you do inside the method. Now we have to be careful about this, and this is one of the reasons that languages like Java will build in certain kinds of synchronized methods and things like that, because it can be hard to remember exactly when you need to release the locks. You are going to do it before you return, but you also need to make sure that you do that before you return false, even in the case where you're not modifying it, because you've actually acquired this, you've acquired the lock either way, and so you need to make sure that you release it. So DQ, it looks very similar. The first thing we'll do is acquire a lock. Then we're going to check in this case to see if the queue has any space left in it. That is, if the head is equal to the tail, then there's no more room in the queue right now. So we will release the lock and just return a -1. Now this is a very hacky way to write a queue, an integer queue. I should really be throwing a C++ exception in this case, as I should have in the NQ, but especially here where I have to make up a kind of a special value -1 that I'm going to return. This is the reason that I'm saying, well, assume that we're only going to put positive or non-negative integers into the queue, so I don't have any possibility that somebody happens to be NQing a -1, which will really confuse the implementation or confuse us as users. And that's not something I'm trying to handle carefully in the, I could have put a check in the NQ to make sure that I wasn't inserting or NQing a -1 or any negative number. So we get the value that's sitting at the head of the queue. We increment the head in order to say, well, that element's already been used, unset the lock, and then return the value that we'd gotten out. There's the pieces of it. And this just shows that once again, we need to make sure in both cases of return statements, we remember to release the lock. Okay, so this is the code again. Can we argue that this code is probably correct in a concurrent setting, that is where threads may be calling NQ and DQ whenever they want? Well, intuitively, the answer is yes, because basically all of the code inside of these two methods is protected by a lock. A lock is the first thing you do in the code. You don't modify anything inside of the queue data structure except when you're holding the lock. And you actually don't read anything inside of the queue data structure except when you're holding the lock. And that's one of the reasons that, for example, over here in the DQ, rather than taking this, I could have put all of this into one statement, statement that said return items of head ++ of and % capacity, all in this statement right here. That would have meant that a bunch of the accesses to shared variables were actually happening outside of the critical region, outside, after the lock has been released. So that's why this value, ret value, is probably sitting in a register. If it's sitting in memory, it's sitting in memory that's private to this particular method, so I don't need to worry about another thread accessing it. So that's intuitively why this code is going to work in a parallel setting and is going to be thread safe the way I've implemented. Now I've implemented in a pretty heavyweight way by acquiring a lock. We're not going to get any parallelism in here. So you may wonder, are there cases in which we could use this queue implementation where we could get real concurrency, that is real parallelism happening inside of the methods. And the answer is yes. In a very constrained situation, if you use the same code but take out all the lock statements, take out the set and unset lock statements, and instead, but in this case, we're going to assume that there's only one thread that's doing any NQ operations and one other thread that's doing DQs. So there's only two threads in the world, and those two threads are going to only access one of the two methods. Not just one of the two at a time, but just one of those two. So one of them is going to do NQ, 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 and the other is going to do DQ, DQ, DQ. And you can imagine why this is actually, although it seems like kind of a simple and maybe uninteresting program, it actually could be useful if you had two threads for whatever reason where one of them needed to share work with the other, but they weren't sharing it more broadly. You could build one of these two reader writer or two threaded queues. And so that's what we'll do, is to talk about a two-thread queue, which is this version of the code that I showed you before, but without any locking in it. It also turns out is going to be what's called a wait-free queue, and we'll talk more about what that means next week, but just to be clear that this is an example of a wait-free two-thread queue. It just has the code that we talked about before. Now what happens, well in this case both of the processors that want to do NQs and DQs can do them simultaneously. So this one that's doing the DQ is getting the return value out. It's looking at items of head, and that's going to be equal to X, which is right here in this data structure. Whoops, this one is doing an NQ, so it's putting something probably other than an X in here, but it's setting items of tail equal to this value, whatever this value is going to be. And then we increment both the head and the tail pointers, though they're not accessing the same variables, and I call them pointers, but they're really just integers, which are indexes into the items array. So in this wait-free two-threaded queue implementation, how can we argue that it's okay for it to not have any synchronization in the code? Well, we can first of all look at these two statements with the pluses in them and ask whether they cause any problems for themselves. So there's both a read and a write of tail here and a read and write of head here. And that's okay because there's only one processor that's going to be doing the reads and writes over here and a different processor that will be doing the reads and the writes over there. So there can't be any erases coming from these two statements alone that will cause on either the tail variable or on the head variable. Now, of course, there's a different problem, which is that both of these methods also read the other variable. So for this processor to read the head variable is not a problem because it's the only one sort of manipulating that variable. So there's no race condition between this head and this head access, but this tail is going to conflict with the one over there. So now we have to think about, well, what happens in this case if we've got processor 1 doing an NQ at the same time the processor 2 is doing a DQ. And we could do this a little bit more formally, but I'll just say if you look at it right now, you could see that what happens is if the head is equal to the tail, that is, there's no space in the queue, there's nothing in the queue to take out of it, we're just going to return -1. It may be that simultaneously, that is right after doing this test, the other processor came along and stuck something in the queue, we would miss it. But we would miss it in a way that, well, at the time that the method ran, it didn't really have anything in it, so it's fine to return -1 in that case, that the queue is empty. So that particular race condition is actually not a problem. Oh, I guess the other case we need to look at is what happens if it falls down here. So it falls down to the rest of the code. Well, that was the case where the head was not equal to the tail. That meant that there was some space, that the head was ahead of the tail. Sorry, that the head was behind the tail. That is, that the tail was sitting over there, had a larger value. And so that meant there was at least one thing in the queue, so we can go ahead and DQ it. And if the other processor happens to be doing an NQ at the same time, it'll just add more elements to it. It'll increment the tail pointer, but that won't affect us down here because we're not actually reading the tail pointer down here. And the value that we read, although it might have been out of date up there, it's not a problem because the only reason we needed to look at the head was to make sure there was at least one element in the queue. And by the time we get down here, there may be there may be 3 or 4 or 6 or whatever, well, up to 8 elements in the queue, but as long as there's at least one, we're fine in executing this code, and that's all we were checking. And similarly, we can make the same argument for this access to the head variable, which is being written here as well as being read, and being read over here. So we've got this read-write race or read-write hazard in the code, and so that could in principle cause a problem. In this particular case, because we're looking at the head up here at the top, and if we decide that the queue is full at this point because the tail is equal to the head, well, then we're going to just return false. Now it could be that the other processor came along and it freed up some space for it right after we did this test. That's okay. We're going to return false anyway, and we'll have to come back another time and try to enqueue something because there was a point in time where the queue really looked like it was full, so we couldn't do the enqueue. And if it comes down here into the code, then it's also okay, because at this point we know there's space left in the queue. If some other dequeues are happening, not just one, but maybe a whole bunch of them, we know that all it's going to do is make more space in the queue. So there's no problem with this. The tail pointer isn't going to change from this other method over here. It'll still have an empty space there at the tail that we can fill in. So these two races are okay, and this is in fact a correct code. So this is a code with races, but the queue still works. But just for the 2-thread case. It doesn't work for more than 2 threads. And the easy way to see that, which we've talked about, I know in lecture and in lab, is that just 2 threads executing either one of these methods is going to have a problem with this statement, because they can, although it looks like one kind of atomic statement that's going to execute just as one instruction, what actually that turns into, as you know, is a read of the tail, an increment in register, and then a write of the register value back to memory, and both of them reading. 2 threads that are both reading this tail index could get the same index value, both add 1 to it and both write it back, and now you're going to have them looking at the same slot to put their element in. Or at least the next time you're going to have a collision. So you will have lost that something in the queue. So what does it mean to have a concurrent queue? So really what we're talking about is we need a way to think about how to specify a concurrent data structure, and specifically in this case a queue. And we need a way to prove that an algorithm implements the object specification. And we've sort of reasoned through it informally, by the way, in the last slide when we talked about why we thought, or 2 slides ago when we talked about why that particular unlocked queue implementation was correct. But we're going to need to figure out a way to do that in general. And what we're going to do is look at how we think about this for abstract data types. Now, most of you have probably never tried to prove formally that a particular data type implementation in a serial program is correct, but hopefully you learned in 61B or even 61A a bit about abstract data types, these classes that are encapsulating things, and what that means and how we can reason about it. So when we think about correctness in a serial program, we really are thinking about 2 correctness properties. One is, does each method return the right result? And the other one is, does each method terminate? I'm sure that you may not think as much about the second as a correctness condition, but certainly if you've debugged any non-trivial programs in your homework assignments in any of your classes, I'm sure you've once in a while run into a case where whatever, you didn't have a base case for your recursion, you screwed up something about your loop bounds or whatever, and your method didn't terminate, or your function didn't terminate of whatever kind you're writing. So in both of these cases, what we're looking at is we're trying to decide for any sequence of method calls, will each of these methods terminate, and will they return the right result? Well, we can't really see from a specification standpoint, that is at the interface level, what's inside of the queue, and we shouldn't have to know. We can look at an execution of the queue and tell whether or not it's a correct execution according to what we believe a queue is supposed to do. So what are the queues supposed to do? Well, it's supposed to put things in and take them out in FIFO order. So we're putting in an X, a Y, and a Z, and we're going to, when we take them out, we're going to get out an X and a Y and Z in that order. So that says that this particular execution is correct. And so the correctness is really about its behavior, about the inputs and outputs, the inputs here and these methods and the outputs that get returned by the DQ method. So in general, this is how we think about the correctness of one of our programs. Now, if we want to prove something about it, we probably will have to look inside the code and look at the state inside of the Q object, that is the items array and the head and the tail and all that, and look at to see whether we can prove that it's correct in general for all possible executions. So in a sequential specification, if we wanted to write down a little bit more formally what a queue is supposed to do, one of the things that we usually talk about is preconditions and postconditions. That is, if the object is in a certain state before you call it, then what is supposed to happen afterwards? And that postcondition involves both what is the state of the object afterwards, and also what is what kind of return values, if any, or exceptions are going to be thrown. So each object has some kind of a state. In the concrete state, inside the implementation, it's given by a set of the fields, let's say the private variables and maybe even some of the public variables inside of that. And in the Q example, we've got a sequence of items, for example. We also have the head and the tail and the capacity variables, and we have the lock. All of those are part of the state of the object. And each of the objects, of course, has a set of methods. And the only way to manipulate the state in a well-designed abstract data type is through the methods, that is not directly by accessing the fields. So for example, through the NQ and DQ methods, once you've constructed the object. And so as long as you make sure those two methods are correct and all of your fields have been declared as private, which we did in this particular case, then we can be guaranteed that for any execution of NQ and DQ, any execution of this Q type, it should be correct, as long as we know that both in the NQ and DQ are correct for any execution order of those two methods. So in a concurrent setting now, it's similar. We also want to know that, that nothing goes wrong in the implementation. We call these safety properties. That means that nothing bad ever happens. What would a bad thing be? Bad thing would be returning the wrong value. That is, for example, returning an element of the queue that was not at the head according to the order in which they were inserted, or crashing, right? Or returning a value that was never put into the queue. Those would all be safety properties or violations of safety properties of a properly implemented queue. A liveness property says that something good eventually happens. That means that eventually your methods, for example, return, that they terminate also. So termination is kind of the simplest and the obvious property of example of a liveness property. So if we try to write our sequential specifications for DQ, just the DQ method, there's a couple of cases. The first one is the precondition is the queue is not empty. If the queue is not empty, it returns the first item in the queue, and it also removes that item from the queue. So even in writing this down, although we don't talk about items as an array, we need to have sort of an abstract notion that there is this type called a queue, and a queue is a FIFO thing. And so that's what we're saying here. And we also have to look at the case where the queue is empty, and the case where the queue is empty, the specification says, well, in my kind of overly simplified version, it will return a -1. Better yet, it might throw some exception. And the post condition in this case is, by the way, that the queue state is unchanged. So just because we called DQ on an empty queue doesn't mean that we get some messed up state of the internal queue. It just means nothing happened. And hopefully the user of that is checking the return value to know that it didn't actually end up NQing the element. So why in serial programs, I know you talk about this, you've heard about this in 61A and in 61B, why is abstraction so great, in particular data abstraction? Because it really means that if you've got a well-implemented, well-designed abstract data type, the user of the object of those type doesn't need to understand the implementation, doesn't need to know that there's 2 pointers, it doesn't need to know that even really exactly what the capacity is. It does need to know that sometimes it might return that there's no more space in the queue, and it can do that based on the specification. And the implementation then can maintain what are called invariants. So these are data type invariants or representation invariants that say that we, for example, know that the tail of the pointer is always supposed to be a larger number, larger than or equal to the head of the queue in our queue implementation. And also that the difference between those two should never be greater than 8, because that's the number of elements that we have in there. And so that will tell us that we haven't sort of overrun our queue in some way. And so those will be invariants that are true. And all the methods can rely on those being true when they're called. And so you could be sure that nobody has somehow stuffed extra elements into the queue, because there's this invariant says there's only 8 elements in the queue, and the head and the tail pointers are preserved in such a way that there's always no more than 8 elements between the two of them. And if it's the case that the queue is empty, then they're going to both be equal. And so we can assume that those are true when the methods are called, and we ensure that they're true when the method returns. Now, the state of the object, by the way, only has to be meaningful between the method calls. And this is a really important property of the way we reason about serial programs, is that within a call, the state may not actually make any sense. That is, we could have mucked around with the head and the tail pointers. We might have written into the queue, but not yet updated, written into the items array, but not yet updated the tail pointer or whatever. So in the middle of the method, we can have the internal state that we can't really think of as an abstract queue object. What this also means is this gives us a lot of flexibility in implementing the methods. And finally, that if we want to add a new method or we want to change the implementation, let's say that we decide we're going to rename head to be tail and tail to be head. Outside of the implementation of the queue, you can't tell what the names of those two variables are, or if the programmer decided for whatever reason, maybe you implemented them the wrong way the first time and you want to swap them later, it shouldn't make any difference in the behavior that the user sees outside. What about a concurrent specification? Well, how do we think about what the user needs to worry about? How do we maintain invariance inside of the data structures? And when do they have to be preserved? And what happens when we start changing implementations, either internally or even by adding new methods? Well, the thing that will change in this case is we're really going to have to think about the fact that methods take some time. So here we've got our little picture of our queue. It's got 2 elements in it. And we've got something that's going to happen over some period of time. So if we've got an enqueue operation, so one processor is calling enqueue, and that happens at some instant in time, it does the call. It's called 12 o'clock, so at noon, it calls enqueue. But the method call has to run for some period of time. And even on a computer, it might be very fast. You might think it happens basically instantaneously because there's very few instructions inside of that code, but it actually does have to execute each of those instructions, which means that things can also be happening concurrently with it. And so that method call takes some time, and so it does its enqueue, and then it returns, and the response comes back as actually it should come back as a true value in this particular case, which is the value that you get back when there was space in the queue. So in the sequential case, methods also took some time, but we didn't really worry about it so much. We don't worry about it from a correctness standpoint. We do worry about it a lot when we're worrying about performance, but in terms of what does it mean for a queue to be correct, we don't really care that it takes some time for a method, because we can think about the fact that we can mess around with the state, but really the only thing that matters is the state when we come in and the state that when we go out of method. In a concurrent execution, a method call is not a single event in time. We can't really think about it that way because things can overlap, and we have to think about it as an interval of time. And so there will be an instant where it starts and an instant where it ends, but not an instant where the whole thing executes. So concurrent methods now take overlapping time. And so we can end up with executions, and it's useful then to write them out this way, where we've got one processor calling a method call, and that can overlap with another method call by another processor, and then that can overlap as well with a third one. And we could even have all 3 of these overlapping with each other. So in a sequential case, we also only worried about the state between the method calls, and in a concurrent state, because the method calls overlap in time, an object has to be meaningful between and during the method call executions. This makes it much harder to implement concurrent data structures. So in the case of our queue, we sort of reasoned through it a little bit in the version without locks to argue that even though we were sort of messing around with the internal state, it was okay if the other thread, as long as there was only one NQ and one DQ happening simultaneously, that we were okay with all the possible ways in which they could happen concurrently. And that's the way we need to really reason about concurrent data structures. And the other thing we can think about is the version with locks, which we can also reason about in terms of the code. But in that case, nothing inside of those methods can really run concurrently. So, and we'll see what that looks like in a minute. Okay, so what does it mean for a concurrent object to be correct? Well, what is really a concurrent FIFO queue? FIFO means that there's a strict ordering on the way in which things are put in and relatively speaking, the way they come out. And concurrent means that sometimes we won't know the order in which things are put in or taken out. So there may be many possible executions in this case of these that, and in some cases it will be a little bit ambiguous as to which element has actually made it in the queue when we look at it from outside of the data structure, that is, and outside of that state. So now we look again at this code with the locks in it. And is this correct for an arbitrary number of processors, not just for two processors as we had before? We could probably guess that because the other one was correct for two processors, one doing NQs and one doing DQs, it would probably also be correct with the locks in it. But as I said, this version with the locks is sort of intuitively correct because all of the interesting code, other than the return statements, which are really returning constant values, false and true in the case of the NQ, and then -1 or a register value that we've already pre-computed, excuse me, in the case of the DQ, are everything else is protected by a lock. So more formally, what does this look like? Well, we can have an execution over time in which the DQ and the NQ are happening concurrently. They overlap in time. And what does that mean? Well, if we look inside of the implementation, we could see these other operations that are actually happening. So the first thing is acquire a lock, and both of them acquire the lock, and then both of them do the unlock or unset the lock in OpenMP. And then there's some code in here that is actually executing the methods that I haven't drawn out each individual statement. And that's because I know that I don't have to worry about the concurrency of those two sequences of statements, whatever they are, whether the NQ or the DQ succeed or fail, because this processor was not able to acquire the lock until this green processor released it, right? The orange one, it tries to acquire the lock, but it can't get it because the green one has already gotten the lock. And so this execution kind of shows you that the interesting parts of the code here are not ever going to overlap in time. And we can think of that by sort of projecting that piece of their execution. So we've got two threads here. One is just doing a DQ and one is just doing an NQ. But the interesting part of the code is happening here in this little time interval for the NQ operation, right? This is where the actual object gets put into the queue. And the other one is where the actual object gets put in or gets taken out of the queue is over here. So this time interval, because of the, we're going to project it down to something that is sequential. And in this particular case, it is sequential. The little green thing and the little orange thing do not overlap because the lock, in any way that we were to write one of these executions, could not overlap in time because the lock has to be held. And by mutual exclusion, only one of them could actually be executing one of their regions. And that's true even if we had two processors doing NQs, we couldn't have two of these little green things overlapping either. Now they could both simultaneously call NQ or DQ, but they can't execute the interesting code in parallel. And so that says that down here, we're going to have a serial execution. And now we can sort of reduce this to a previously solved problem of how do you reason about code, because we know what NQ and DQ are supposed to do on a FIFO queue. More formally, what we'd call this in concurrent data structures is linearizability. That means that each method appears to take effect instantaneously. It's in that little sequential, that little interval that can map onto a sequential timeline. And so we can't have any ambiguity when they get mapped onto that sequential timeline. And the other condition, which is very important in linearizability, is that instantaneous point in time where the method took place was sometime between the invocation and response events. And what does it mean for it to appear to be instantaneous? It means that all of the threads have to agree on where that operation took place. We can't have one thread that thinks the NQ happened before the DQ and the other thread thinks that it happens out of order. Or maybe a better example is if you've got two threads that are simultaneously NQing something, one is NQing X and the other is NQing Y, they all have to agree on what the first element of the queue is. And we'll see that now. We'll look at some examples. And the concurrent behavior of the queue is, the sequential behavior also has to be correct. What does that mean? It just means that when we map it onto that serial line, it's got to behave like a FIFO queue in this case. And any such concurrent object is considered linearizable, which is a trademarked term, actually. Okay, so here we've got example number 1. We've got our little queue. We've got multiple readers and writers here. So this is not the case where we've only got one reader and one writer, although we'll only have a couple threads just to make it simple. But we've got one thread that is doing an NQ. And simultaneously, exactly what I talked about a minute ago, another thread is also doing an NQ. So if a thread comes along and does a DQ, and it gets an X out, which is the value that was put in by the first thread, is that okay? It didn't see its own value that it put in. Instead, it saw the value that was put in by the other one. And now the first thread also comes along and does a DQ, and it gets a Y out. Okay, so now there's some things we know would be a problem here. If this thread got Z out and Z was never put into the queue, that would not be linearizable because it's not a sequential, it doesn't map onto any kind of serial order that says, oh, you can just make up some random value and get it out of the queue. And it can't crash, but these functions are actually returning. And so now the question is it okay for this particular order to happen? And the answer is yes, that this is linearizable. And the reason is because we can pick an instantaneous point somewhere in the execution of each one of the methods at which it looks like that method occurred. And we don't really need to go and look at the code. We can look at the fact that in this timeline, these two NQs were happening simultaneously, overlapping in time. They started together. But we can just assume that because we see how this execution unfolds, that the X gets NQ'd first. And so this little purple line is before this little red line, because this one's instant is right here in time, and this one's instant is right there, and the two are ordered in the timeline down here. And then similarly, when the DQ happens, it's going to DQ the X. So even though it's not from its own thread's value is Y, we're going to get the one that was put in first up here, and this one is going to get in the value that was put in second. So this is a linearizable execution because we can come up with some way of identifying some instantaneous points in which they kind of all agree on what those instantaneous points are. That is, this one didn't get an X out and this one also got an X out because they disagree on which one was first. They have to all agree on that. So let's look at a second example. What about the other way around? What if the DQ, so there we again have X and Y being NQ'd simultaneously. Now we have the first DQ that happens is going to return Y, and the second one is going to return X. Well, that's also fine because in this case, as long as it's in the middle of the execution here, we could assume that this processor runs a little bit faster, the red one, and it does the NQ before the purple one does its NQ. So when the red one does its DQ, it gets out the Y that it put in itself. And similarly then, that when the later DQ comes along, it has to see the value that hasn't yet been taken out of the queue. So this is also linearizable. What about another example? So let's look at the case where we've got an NQ happening and a DQ happening on this one thread. And simultaneously with that DQ is another NQ by the second thread. So it doesn't overlap with the NQ, it overlaps with the DQ in this case. So what are the values that we can get out of this or will this particular one make sense? So this is getting out, this is doing a DQ of Y. and this is doing an NQ of y. Now we know from the previous example that it's okay for these two things to execute concurrently, and we could just say, well, we're pretty sure this one happened instantaneously earlier than the purple one. The red one, the NQ happened before the DQ, so that would be okay. Except it's not okay in this particular execution, because in this particular case, the DQ, we can try to find these instantaneous points for the two NQ operations, but we can't in any way make this NQ, the X, happen after the Y, because in this particular execution, these two things do not overlap in time. There's a gap between them, so there's no way to turn this into kind of interpret this as a linearizable execution. And this one, because it returns a y, it says these two NQs have to happen in the opposite order. So this is not linearizable. Okay, let's see one more example here. If we're doing a NQ operation and it's still pending, and we've sort of talked about this before, if it's still pending, then if we do a DQ in an ongoing operation, it's okay for that DQ operation to see the NQ operation happening, as long as something else hasn't happened that tells us that that there's something else in the queue. So in this particular case, there's nothing else in the queue, there's nothing else in the execution before this, so it's okay for that DQ to happen. And so this one is indeed a linearizable execution as well. By the way, we can move this purple thing anywhere in here. So we could also assume that if the DQ returns something else, for example, the DQ returns -1 because because the queue is empty, that would be a perfectly legitimate result as well. Okay, so let's look what happens once again when we have NQ operations that are concurrent, they're overlapping in time, a DQ that says, oh, the first thing that won here was this the red NQ of y, and the second DQ is the NQ of x, and that one is linearizable as well. But it turns out, and we looked at that execution before, but it also could be, there's actually multiple ways we can look at this execution. So we can look at the one in which the x got NQ'd first, y second, and x got DQ'd first and y second. Is a little hard to tell. These lines should be a little further apart here, but basically this red DQ has happened before this purple DQ. We can also assume that the y got NQ'd first, but in that case the y DQ has to happen before the x. And so that it's okay for there to be two different interpretations of how these two things are linear. This particular execution is linearizable as long as there's at least one. So why in this case are we talking about executions? And the reason is because we can't really talk about what the linearization point is of each operation without talking about a particular execution. And you sort of saw that because you saw that if we put an NQ, for example, in front of something, then we needed to make sure that if we had two overlapping things, an NQ and a DQ, that the DQ couldn't ignore the fact that there was something that had already happened. It can't just pull out the thing that's in the queue that's being inserted at that point in time. And sometimes we'll find that that linearization point, therefore, does depend on the total execution, not just what is happening, say, in a given instant in time, or what's happening inside of that one particular method. All right, well, with that, we'll end this introduction to linearizability. I will talk about it more in the next lecture, and also we'll give some more examples, and we'll talk a little bit more also about other ways of thinking about correctness and why this particular idea of linearizability is one that's very popular for thinking about concurrent data structures. Thanks very much.